Hello. Hello students, my name is Sumit Sagar Hota. I'm a PMR PhD student at IIT Palakkad. Okay. This is the week 7 of the live discussion section. In this section, we will cover lecture 31 to lecture 35 by Professor Ashok Desai, IIT Kanpur, of the subject Introduction to Airbreathing and Propulsion. Okay. I already shown you the questions what we are going to solve today. Okay. And hope you just try solving this question. Okay. Meanwhile, we just go through the MCQs, and at the end we will solve this question. Okay. Okay. So the first question is, in a turboprop engine, the expansion of gas takes place partly in dash and partially in dash. Okay. So the answer is, in a turboprop engine, the expansion of gas takes place partly in turbine and partly in nozzle. Okay. 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 So the dash percent expansion takes place in the turbine and dash percent expansion takes place in the nozzle of a turboprop engine. Okay. Basically, the maximum expansion obviously takes place in the turbine, and the rest will takes place in the what? Nozzle. Okay. So the maximum is 80% expansion takes place in the turbine. Okay. And this is your 20. Okay. And write down another way. And 20% expansion in nozzle. Okay. The turboprop engine can operate economically over a wide range of speeds. True or false? It's absolutely true statement. Okay. The frontal area in turboprop engine is more than in propeller engine. So the drag is what? Reduced. Is it a true statement or false? It's absolutely false statement. Okay. So the frontal area of turboprop engine is always less than the frontal area of propeller engine. Okay. So the frontal area of turboprop engine is less than the frontal area of the propeller engine. Okay. Next question. In a turboprop engine at high speeds, the propeller efficiency is dash. Okay. I already told this kind of statement. For the propeller efficiency is inversely proportional to the velocity of flow velocity. Okay. Okay. So the turboprop engine at high speed, the propeller efficiency will what? That means if the speed will increase, the propeller efficiency will what? Decrease. Okay. This is your answer B. Okay. So the reduction gear exists in turboprop engine. True or false? Yes, reduction gear exists in the turboprop engine to increase the efficiency. Okay. The reduction gear in turboprop engine is dash the cost and consume certain energy. Yes. Because it's actually extra component, so obviously because of addition of this gear mechanism will having some extra cost will be involved. Okay, and it's obviously consume some extra energy. Okay. Including the reduction gear in turboprop engine, your cost of engine will increase. Okay. Energy consumption. Energy consumption will increase. Okay. The turboprop engines are widely used in dash. The turboprop engine can be used both in commercial and military aircrafts. Okay. The turboprop engine can be widely used in commercial aircraft and military aircraft. Okay. The turboprop engine is very flexible and having good fuel economy. This is obviously a true statement. Okay. So the flight speed of turboprop engine is dash is a 400 to 600 kilometer per hour. Okay. Okay. So the flight speed of turboprop engine is 400 to 600 kilometer per hour. Okay. The Rolls-Royce developed a AE2100 based on the T56 but the free power turbine. Okay, with a free power turbine with an output of dash kilowatt, and this was used in C-130J and C-27 military transport. Okay, so this answer is actually C. Okay. Okay. The output power of AE2100 is 4500 kilowatt. Okay. The turboshaft engine in which the output power drives a rotor. Okay, dash rotor. Okay, it's a helicopter rotor. Okay. Helicopter speeds are limited to about dash knots. Okay, it's 160 knots. Okay. So Rolls-Royce 250 and PwC 200 turbo shafts uses a dash. It's a centrifugal compressor. Okay. The turbo shafts always uses a what? Centrifugal compressor. Okay. Yeah. Okay. So Rolls-Royce 250 and PwC 200 turbo shaft, limiting the cycle pressure ratio to about dash. Okay. So for turbo shafts, the pressure ratio are not that much high. Okay. Because they use a centrifugal compressor. Okay. So it's about 9. Okay. Okay. So T800 jointly developed by Rolls-Royce and Honeywell turbo shaft uses dash. Okay. It's a two because we know already know that Rolls-Royce uses the centrifugal compressor, but it's a two-stage centrifugal compressor. Okay. Okay. Because this turbo shaft always uses a centrifugal compressor. Okay. Okay, a jet propelled plane consuming air at a rate of 18.2 kg per second is to fly at a Mach number of 0.6 at an altitude of 4500 meter. PA and TA at the ambient condition are given. That is 0.5 PA is 0.55 bar and TA is 255 Kelvin. The diffuser, which has a pressure coefficient of 0.9, decreases the flow to a negligible velocity. The compressor pressure ratio is 5 and maximum temperature in the combustion chamber is 1273 Kelvin. After expanding in the turbine, the gases continue to expand in the nozzle to a pressure of 0.69 bar. The isentropic efficiency of compressor is 0.81 and the end of a turbine is 0.85 and nozzle of 0.915. The heating value of the fuel is 45870 kilojoule of per kg. Okay, assuming Cp as 1.005 and Cpg is 1.147 kilojoule per kg Kelvin, gamma of air is 1.4 and gamma of gas is 1.33. Calculate the power input to the compressor, power output of turbine, fuel air ratio, thrust provided by the engine, thrust power level out. In the question, T4 also, T4 is already given 1104.125 Kelvin given. Okay, so let's start solving. So let's start solving this question. First of all, draw the cycle. Okay. So this is a 1 and 1 dash. Okay. So 1 to 2 there will be compressor work. Okay. A to 1, ambient to 1, there will be ramming. Okay. 3 to 4 there will be Warden in the nozzle. And 4 to 5 there will be Warden in the okay. Obviously there is no Warden in the nozzle, so just write down nozzle. Okay. Okay. Similarly there is no Warden in the ramming, so we just only we write down ramming. Okay. So this is a complete cycle we have done. Okay, now it becomes next we just mention the heat addition and heat rejection. Okay. Okay. So this is your Q add and this is your Q reject. Okay. So let's start. solving. So efficiency of the compressor is given 0.81. Efficiency of the turbine 0.85. Efficiency of the nozzle 0.915. Okay, let's find out the T1 dash. Okay, so what is T1 dash? T1 dash is equal to TA plus VI square by 2CP. Mach number is equal to 0.6 is equal to VY by square root of gamma R TA. Okay, is equal to, we need to find out the VI. Okay, so VI divided by 1.4 into 287 into 255. Okay, so it will be VI is equal to 192.06 meter per second. Okay. Okay. So what is T1 dash? Because we have everything. Okay, let's substitute and find out the T1 dash. The T1 dash is equal to 255 plus 192.06 square divided by 2 into 1.005. So T1 dash is equal to 273.35 Kelvin. Okay. So diffuser coefficient, ramming efficiency. Okay, what is the ramming efficiency given? 0.9. Okay, which is equal to P1 minus PA divided by P1 dash minus PA. Okay. So the dash always represents the ideal case, and the without dash or without prime is always represented by the actual case. Okay. So it's actual to the ideal. Okay. That's the reason it's less than 1. Okay. So let's apply the T and TP relation. Okay, to find out P1 dash, because everything we have in between TA and 1A and 1 process. Okay, except P1 dash. Okay, so, and if we have P1 dash, then we just substitute in the ramming efficiency and find out the what? P1. Okay, so just apply T ideal, the isentropic relation of TP So P1 dash is equal to 0.70144 bar. Okay. So just substitute here and find out the P1. Okay. So 0.9 equal to P1 minus 0.55 divided by 0.7014 minus 0.55. Okay. So P1 is equal to 0.6863 bar. Okay. So now next we just need to find out what T2 dash. Okay. So okay, what is the compressor efficiency? The compressor efficiency is equal to 0.81 is equal to T2 dash minus T1 divided by T2 minus T1. Okay. Okay. So yes. So so here from this formula we need to calculate what your T2. Okay. So just let's apply the isentropic relation between the T2 dash and T T2 sorry 2 and 1 2 dash and 1 or 1 to 2 1 to 2 dash process, the TP relation, isentropic TP relation we need to apply to find out what T2 dash. Okay, let's apply. So T2 dash by P2 dash to the power 1.4 by P2 to the power 0.4 is equal to T1 to the power 1.4 divided by P1 to the power 0.4. So T2 dash is equal to T1 is your what 273.35 Kelvin. So T2 dash is equal to 273.35 into P2 by P1 we know already 5. Okay, to the power 2 by 7. Okay, P2 by P1 is equal to 5. T2 dash is equal to 432.94 Kelvin. So just substitute this in the isentropic compressor efficiency. Okay, okay, your efficiency of the compressor. Okay, so T2 the 432.94 minus T1 is here 273.35 divided by T2 minus 273.35. So T2 is here 470.4 Kelvin. Okay. Okay. So let's find out the work done by the compressor. Okay. Because we have T2 and T1, just let's find out the work done by the compressor. Okay. Okay, so W is equal to m dot Cp T2 minus T1. Okay, so m dot is here 18.2, Cp is here 1.005. So 470.4 minus 273.35. Okay, so W is equal to 3603.713 kilowatt. Okay, so just now let's balance the heat addition. Okay, in between 2 and 2 to 3 process. Okay, because T3 already given in the question 1273 Kelvin. Okay, the compressor pressure is 5 and the maximum temperature in the combustion chamber is what? 1273 Kelvin. Okay, which is your T3. Okay. Okay. Just write down the heat balance. So m dot A into 1 plus F into CPZ into T3 minus m dot A into CPA into T2 is equal to m dot A into F into Cv into combustion efficiency. Okay. Okay. So m dot A and m dot A got cancelled. Okay. So from here we can actually calculate F. 1 plus F into CPG already we have 1.147 into 1273 minus CPA 1.005 into 470.4 is equal to F into calorific value of the fuel 45870, combustion efficiency taken as 100% efficiency 1. Okay, from here we can calculate the F value, which is 0.0223. okay, which is your what, fuel air ratio. Okay, In the question they asked the what is the fuel air ratio. This we now calculate. Okay, calculated. Okay, your answer. Okay. So that means from this fuel air ratio we can calculate the what? Your m dot f. Okay. Because we already have m dot a. Okay. Now where is given m dot a jet propelled plane consuming air at a rate of 18.2 kg per second. Okay, is to fly Mach number this. Okay, so that means m dot a in the question given as 18.2 kg per second. So f is equal to m dot f by m dot a is equal to implies m dot f is equal to 18.2 into 0.0223. Okay, so m dot f is equal to 0.405 kg per second. Okay, so we have m dot a, we have m dot f, we have T3. Okay, and T4 already given in the question. Okay, so we can easily now calculate what the turbine work. Okay, let's calculate the turbine work. M dot a plus m dot f into CPG into T3 minus T4. Okay, so m dot a into 1 plus f into CPG into T3 minus T4, which is your 18.2, 1 plus 0.0223 into 1.147 is 1273 minus this 1100 4.125 Kelvin. It's already given in the question. Okay, so when you solve it, you get WT as 3603.713 kilowatt. This is your second bit answer. Okay, so second bit answer we have the power output of the turbine. Okay, let's calculate other quantities. Okay, so let's consider the turbine efficiency. Okay, which is T3 minus T4 divided by T3 minus T4 dash, which is 0.85 is equal to 1273 minus 1104.125 divided by 1273 minus T4 dash. Okay, so the T4 dash will be 1074.32 Kelvin. Okay, because 4 dash is your what? 4 dash is your actual cycle, right? Sorry, 4 days is your ideal cycle. Okay, so 4 days is your what? Ideal cycle, and 4 is your actual cycle. So unless and until you know the T4, we cannot calculate the T4 dash. So it's required in the question to give the T4 value. Okay, otherwise it's very difficult to calculate T4 dash. So now we have T4 dash. Let's calculate the ratio of pressure ratio in the turbine. Okay. Okay, the next thing what we need to calculate is the thrust provided by the engine and the thrust power developed. Okay, the thrust power and the thrust force. Okay, these are the two things we need to calculate next. Okay, we know very well the thrust power will be the thrust force into the inlet velocity. Okay, vi. Okay, F into vi is your power. Okay, so that means we need to calculate now the thrust power. Okay, and for calculating thrust power, okay, we need the exit velocity. Okay, or the velocity through the out from the nozzle, the inlet velocity. Okay, and the nozzle area. Okay, the critical pressure and the ambient pressure. Okay, m dot a and f value, the fuel air ratio we already have. Okay, so let's find out the pressures. Okay, P4 dash and the P critical pressures. We have T4 dash, so just apply the isentropic relation to find out P3 by P4. Okay, here in the 3 to 4 process, so it is the gas condition, so we need to apply the what, gamma of gas. Okay, which is 1.33. So T3 we have already 1273 Kelvin. T4 dash we have already 107.4.32 Kelvin. Okay, so here if you substitute all this value and take the ratio P3 by P4, you will get the ratio at the turbine RT is equal to 1.98. Okay. Okay, so we need to calculate what? Sorry, P3 by P4 dash. Okay, so we know what is P3 already. Okay, okay, in the question it's given that after expanding in the turbine, the gas continue to expand in the nozzle to a pressure of 0.69 bar. Okay. 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 So just substitute this value. Okay. Okay, so okay, one thing we already know is that one thing we know that P2 equal to P3 and P2 by P1 is what? 5, we know. Okay, so P2 is equal to P3. Okay, and what is P2? Is P1 into R. Okay, okay, or RC you write down. Okay, compression ratio. Okay, so this is P1 is your what? 0.6863. This is your 5. Okay, this is bar. Okay, so just substitute here. Okay, so P4 dash is equal to 5 into 0.6863 divided by 1.98 is equal to 1.732 bar, which is equal to P4. Okay, P4 dash and P4 pressures are what? Same. In the cycle you can see the pressure, both pressures are same. Okay, 4 and 4 dash. Okay, so there, just let's find out the pressure ratio in the nozzle. Okay, the pressure ratio in nozzle is what? P4 dash by PA is 1.732 bar divided by PA is your 0.55. Okay, okay, PA already you see in the question it is given 0.55 bar, TA 255 Kelvin. Okay, so I just substituted the PA value and take the ratio. Okay, P4 dash by PA, if you solve it you will get 3.1486. Okay, now what is the critical pressure ratio? Let's calculate. The critical pressure ratio is P4 by PC, okay, which is 1 by 1 minus gamma minus 1 divided by nozzle efficiency into gamma plus 1, okay, to the power gamma by gamma minus 1. Okay, the efficiency of the nozzle is 0.91 and gamma is 1.33. Okay, so if you solve it you will get it as 1.97. Okay, so it's actually greater than the critical pressure. Okay, So P4 the pressure in the nozzle is greater than the critical pressure ratio, so the nozzle will what? Choke. Okay. Because it's higher, the pressure ratio is higher than the critical pressure ratio value. Okay, so there is a chances of nozzle choking. Okay, let's find out the critical pressure ratio critical pressure value. Okay. Your PC is equal to P4 by 1.97. P4 is 1.732 divided by 1.97. PC is 0.8794 bar. Okay, this is your critical pressure. Okay, what is TC? Okay, your TC is your 2 by gamma plus 1 into T4 is 2 by 2.33 into 1104.125. Okay, so if you solve it, you will get TC as 947.75 Kelvin. Okay, so this is your critical temperature. Okay, so now you have the critical temperature. That means you can calculate the velocity of the what? Jet. Okay, that is Vj. You can calculate. Square root of gamma r Tc. Okay, what is your gamma? 1.33. R is your 284.6 into 947.75. Okay, okay. The velocity of jet is 598.95 meter per second. Okay, okay. Vj you have now. Let's calculate the rho c. Rho c is your Pc by RTC 0.8794 10 to the power 5 in Pascal. I just converted, and R is your 287.6 into TC 947.75. If you solve it, you will get 0.326 kg per meter cube. Okay, you know one thing, MA plus MF is equal to is your rho C into area of the nozzle into Vj. Okay, so nozzle area is equal to what? This is your what? Ma into 1 plus f. Okay. Nozzle cross sectional area is equal to what? Your 18.2 into 1 plus 0.0 triple 3 divided by your rho C 0.326 into Bj 598.95. So AN is your 0.0953 meters square. Okay. So AN we have. Let's calculate the thrust. Thrust force provided by the engine is equal to F is equal to okay. So F is equal to Ma into 1 plus F into Bj minus Bi plus An into Pc minus Pa. Okay. This is your what? 18.2 into 1.0 triple to 3 into 598.95 minus 192.06 plus 0.0953 into 0.8794 minus 0.55 into 10 to the power 5. So F is equal to 10708.78 Newton. So here fourth bit answer. Okay. So the thrust power is equal to P is equal to F into Vi is equal to 10708.78 into 192.06. So P is equal to 2056.7 kilowatt. Okay. This is your fifth bit and answer. Okay. Thank you very much for attending the section. If you have any doubt, you can ask in my YouTube channel. My YouTube channel is Sumit Sagar Hota. See you in the next week with the lecture 8. Okay, we'll meet next week 6 to 8 p.m. Saturday. Okay, thank you. Have a nice day and good night.